So the video lessons on energy and pointers to the book chapters and pointers to my notes from last fall on energy are all posted up under remote lecture materials. But I wanted to talk about a few specific things and do a new different example just so you have a little bit more to go off of. So the first thing I wanted to mention is something that always comes up, and that is the relationship between work and potential energy. To me, these two ideas are different ways of representing the same thing. They're different ways for accounting for how a particular force affects the energy of an object. So the one way we have is work. And what we do with work is work changes kinetic energy. This equation is often written as work is equal to delta K. And what you do with a delta quantity is you add it to the initial quantity. So I took some gravitational work here and some other work, maybe due to friction or some applied force, and I added it to the initial kinetic energy in order to find, or at least write an equation for the final kinetic energy. So that's one way the energy balance equation might look. You have some initial, add the work, and then that gives you the final. But another common way to deal with especially gravity, but some other forces, is to account for gravity using potential energy. So UG is gravitational potential energy. And U sub G is equal to mgy. So you take the weight of the object, that's the mg, multiply it by your y value. Wherever you set the origin is fine. You just measure y values from there, and that is your U sub g value. And the way potential energy works is it gets added to kinetic energy. This combination here is called mechanical energy. The combination of kinetic plus potential is mechanical energy. So since we've accounted for the work due to gravity, we don't add that anymore. That's part of the U value. But we still have to account for the other work. So that gets added in, and that gives us the final value of our total mechanical energy, which is, again, kinetic plus potential. And I wanted to show how these really are the same thing. So if you take this equation, I call this the non-conservation of energy because often we talk about conservation of mechanical energy, that is the K plus U value initial is equal to the final. But if you add in some other work, then it's not conserved. You got energy from somewhere else, or you lost energy to somewhere else. So that would be part of the work other. So I took this and I subtracted UGF from both sides, so it pops up as a negative over here. And then I recognized that this difference is the delta of this UG value. But it's not how we usually calculate the delta. Usually a delta is final minus initial. This is initial minus final. So it's actually the negative delta. So now that we see that this is the negative delta, we have two equations, and they both have a K initial eventually plus work other equals K final. And the top one has a work gravity, and the bottom one has a negative work, negative delta UG. So that is why the work due to gravity is minus the change in potential energy due to gravity. I did a graphical version of that in the notes last year in, I think, lecture 22. So you can see the graphical version of those same equations. Now, when you're doing energy analysis, you want to account for gravity using either the potential energy of gravity, mgy, or the work due to gravity. You don't generally use both of those things in the same equation because it would be accounting for the same thing twice. And we'll talk about springs probably next Monday. We'll talk a little bit about springs. I think that's in lesson 23. That'll get posted to our playlist. And springs also do the same thing, where there is a potential energy function. And when you rise due to gravity, you have to give gravity some energy. So it's taking energy away from you. But when you come back down, you lose gravitational potential energy. Gravity gives you that energy back. It doesn't have that energy anymore. Gravity doesn't have that energy anymore. It's giving it back to you. So as you fall, you are gaining kinetic energy from gravity. So that's the first thing I wanted to talk about. Anybody have any comments or questions about that before I move on? Okay. The next thing is a little bit about the math we could do. The definition of work, the formal definition, isn't just a force times a distance. It is an integral of force through a distance. And that gives us the freedom to have a force that doesn't have one particular value. Because if you had a fluctuating force, would you use the minimum value of the force or the maximum value of the force or like a middle value of the force? Well, doing an integral allows you to use all the values of the force. And at each point along the integral, you just find the value of the force at that particular point. The idea of work also involves the relative direction between the force and the motion. So as you're moving an object from this initial point up to this final point, the motion path keeps changing direction. That means that sometimes the path is exactly opposite to the force if your path is going straight up. Sometimes your path is perpendicular to the force, and your path can even be in the same direction as the force. It just depends on where along the path you are and what kind of a path your object is taking. So while your object is moving under the influence of a force, if theta is less than 90 degrees, that means that the work contribution called dW is positive. And if theta is greater than 90 degrees, that means that the work contribution called dW is negative. Now we'll look at a case where the theta is constant, and the nice thing about constants and integrals is you can just pull constants outside of integrals. So that'll make our integral a lot easier to deal with. So we'll talk about a case with, well, I think it's in the lesson, I talk about a case with a ramp and an object moving down a ramp. Now I wanted to relate that to what I just talked about up here, that work is minus the change in potential energy. So that means if you have this nifty integral that you can use to calculate the work due to a force, I guess my force is capital F, then you can use the exact same integral to calculate the change in potential energy. It's just that you have to use the negative integral. And when you're talking about work, or when you're talking about a change in potential energy, you're talking about a process, a definite process that goes from one place to another. Your object follows a path from one place to another. At the initial point, there's an initial time. At the final point, there's a final time. And that can all be described mathematically. The cool thing about potential energy is you can define the idea of potential energy without a definite path. So you take away the boundaries here and call it an indefinite integral, and all of a sudden you have a way of defining a function u, the potential energy function for a particular force. And that's how we end up defining u sub g as mgy. Now, of course, if potential energy is minus the integral of force, then it should go the other way around also. And one of the tricky parts about this is potential energy is a scalar, a regular function, whereas force is a vector. So we need to have some way of turning a number, capital U, into a vector. And the way we can do that is we can take the derivative of the potential energy with respect to the x motion and relate that to the x component of force. The derivative of our potential energy with respect to y motion gives us the y component of force. So that means if u sub g is equal to mgy, then fgx is negative partial by partial x. And a partial derivative like this is very similar to a regular derivative, but with a partial by partial x, we assume y is constant. So m is constant, g is constant, y is constant. That means this comes out to be 0. And fgy, the gravity y component, is minus partial by partial y of mgy. Well, the m and g pop out of the derivative. The minus sign is still there, so we get minus mg, and then the derivative of y with respect to itself is just 1, so I don't need to write anything. And magically, we have the components that we already knew for the gravity force. So that's the relationship between potential energy and force. So far, so good. Now, the last thing I wanted to do as part of a lecture type thing today is I wanted to do a full-on example where I talk about everything that I think during the example. So here's the example I picked. It's out of the back of the chapter, and it involves a bike ride that has a hill. So we're going to have a road here with a hill at the top. And initially, let's see, what's a bike look like? Yeah, that looks like a bike. So initially, we have some VI, and at the top of the hill, we are not going to be going as fast. So we're going to have a VF. And as part of the process of getting from the beginning to the end, we're going to have some force of static friction that's going to propel the bike up the hill. So let's see what we can calculate here. Initially, K initial is 1/2 mv initial squared. So that is 1/2 times 85 kilograms times 6.0 quantity squared. So K initial is a number. 25 times 85 times 6.0 squared. 1530 joules. Now, at some point, we have to make a decision whether we're going to think more about work due to gravity or the potential energy of gravity. And when we're talking about external work, this is including gravity. So gravity is not stored in an object. Gravity energy is actually stored in the universe's gravitational field. So that doesn't count as part of our system. If you consider the Jonathan bicycle Earth system, then you might think of the gravity between Jonathan and the Earth as being part of that. But technically, the gravity is not part of just our person. So as part of our process, the work due to gravity is Fy delta y. So the easy version of work is just force times distance. And the thing you have to make sure you take into account is that you want the force and distance to be measured in the same direction. So either the force or distance is the direction you're thinking about, and the other one you have to take components of it. So if we think about the y direction, we have some y motion here, which is upward, and we have a y force. So this is minus mg delta y, which is minus 85, 9.8, and then our delta y is the height. So that's delta y, 7.3. 85 times 9.8 times 7.3 is 6081, minus 6081 joules. And we're going to have work due to S, that is the force of propulsion, which is actually a friction force. Technically, it's a static friction force, but we don't know it. Now we can think about the final. A final is equal to 1/2 v final squared is 1/2 m is 85. V final is 1.0 squared. So this is half of 85 is 42.5 joules. So in climbing this hill, this bicyclist slowed down a lot because the hill is difficult. So how's this fit in to our idea of an energy balance equation? Well, we should do K initial plus work net is equal to K final. So we have our 1530 joules plus the work due to gravity is minus 6081 joules plus work due to static friction. It's really internal work, but I'll call it WS. It's energy released by the person's body that turns into mechanical energy because of the static friction force. I guess that's a pedantic way of putting it. And then we have the final energy is Kf is 42.5 joules. So I'm just going to take my 42.5, subtract my 1530, and add my 6081, and I get 4603. So my work internal is 4603 joules. There's a technicality about static friction forces. The point of contact isn't moving, so the energy comes from inside the object. People have muscles, cars have engines, and that exerts a force which causes the ground to exert a force back, which is also the static friction force. And that's what allows the energy to, actually, let's say, allows it to be transferred to the object as work. So it was internal energy, and because of this grip on the ground with static friction force, it becomes work, and work contributes to the chemical energy, and that's this W sub S. So what is the total external work done on the system between the time he starts at the bottom and the time he reaches the top? Well, that would be this part. So total WEXT would be both of those together. That's part A. Part B, what is the change in potential energy stored in Jonathan's body during the process? I would say that is this W sub S. I don't like this term, but Jonathan's body loses, this person's named Jonathan, okay, loses 4603 joules during this process, and that means that Jonathan has to do 4603 joules of work in the process. So the delta U internal is equal to minus 4603 joules. And that W, that delta U internal is W, which I call W sub S, is minus delta U internal. That is part C. So that is an introduction and example of potential energy and work. So you can use that to supplement the video lessons and the reading of the textbook. Don't forget to read the textbook in order to help you figure out how to attack physics analysis using the idea of energy.